All right, so we're going to pick up on our little chapter 2 where we're talking about buffers, and we didn't quite get to finish this in class. So let's talk about it here. So number 4 is kind of where we left off. And the question is, if we have a buffer that has equal amounts of weak acid and conjugate base, how's pKa related to pH? And so if you know you have equal amounts, that's telling you that if this is Henderson-Hasselbalch, right, that this ratio right here, this is equal to 1. So what's the log of 1? We know the log of 1 is 0. So that's pH is equal to pKa plus 0. That means pH is equal to pKa. So if a buffer is made so that the amount of weak acid is greater than the amount of conjugate base, what would be the impact? So if we increase the amount of weak acid, what's going to happen? So that would mean that HA would be greater than A minus. So this unit down here at the bottom would go up and this one would go down. So what would your effect be on pH? Well, in that case, our pH would drop, right? If we have more acid, your pH is going to drop. And the reverse is true as well. So if we have the opposite, where we have more of the conjugate base, then what's going to happen? Our pH will increase. Okay, so that was not too bad. Then we have kind of a little more complicated one. Whoa. Okay, on number 5. So here we're talking about blood plasma, and this is how blood plasma works, right? We have HCO3 minus and carbon dioxide inside of your bloodstream. And so what's going to happen is that those two are going to combine and you're going to get H2CO3, right? And so when you have H2CO3, the H2CO3 can then dissociate into HCO3 minus and hydrogen ions, right? And so you can monitor the pKa of this, and the pKa of that dissociation, the pad would stay still, is 6.1, right? So because we're making the H2CO3 in the blood all the time, right? And it's catalyzed by an enzyme that's found in your bloodstream, and it's in your book. But because this is going on all the time, we can consider carbon dioxide a conjugate acid, right? And then HCO3 minus is going to be the conjugate base in our buffering system. So the question is, what's the ratio of our substituents? What's the ratio of HCO3 minus and CO2 in our blood plasma at, let's just say, pH 7.4, because we're supposed to be pretty close to pH 7. So what you need to do is remember your formula. pH is equal to pKa plus the log of A minus over HA. Okay, so just plug in your values. We know that the pH in the blood right now is 7.4. We know that our pKa is 6.1. Now, you have to make sure to plug the right things in the right place. So be very careful about that. And this one's going to be CO2, and it's aqueous, but I'm not going to worry about putting it on this. So then just do your math. You're going to subtract 6.1, right? 6.1. And you're going to get the log of this same ratio, right? So when I'm trying to figure out the ratio, I don't actually have to put in values, right? So I can just copy this, paste it in, right? It's the log of that. It's the same thing. So in order to get rid of log, what are you going to do? To get rid of log, you just take 10 to the. So do the same thing on both sides to get rid of the log. So that cancels. So 10 raised to the 1.3 is going to be 20, is equal to our ratio. And so what you can then do is just say that's 20 to 1, right? So now we have a ratio. We got our ratio of HCO3 minus to CO2. Now, B says, what are the individual concentrations under the same conditions? Well, now this gets a little bit tricky, right? So what you have to know is how much total is in the solution. Well, we said that right up here, right? This is our total carbonate pool. This is everything that we have. So our total carbonate is 0.025 molar. Well, what's your total carbonate composed of? We have our HCO3 minus, and we have CO2, right? Okay, so what else do we know? The other fact that we just figured out was HCO3 to CO2 was a 20-to-1 ratio, right? So if we take this second thing right here and we solve for our HCO3 concentration, right? So that's HCO3 is equal to 20 times our carbon dioxide concentration. Now, take this that we just solved for and plug it in right up there. I need my sign there. Plug it in right up there. So then I get 0.025 molar is equal to 20 times my CO2 concentration plus my CO2 concentration, right? So now you just have to factor out the CO2 and you get 20 plus 1, right? Then we want to get rid of the 20 plus 1, right? So then what do you get on this side? You get 0.025 molar over 21 is equal to our CO2 concentration, which is equal to, if you put it in your calculator, 1.19 times 10 to the minus 3 molar, okay? So when we get that, right, that's our CO2 concentration. So what we want to know is the concentration for both, right? So we need our HCO3 minus concentration. So just plug it into the formula above, right? Our maximum was 0.025 molar, which is 2.5 times 10 to the minus 2 molar, right? Minus 1.19 times 10 to the minus 3 molar. And so what you get should be 2.38 times 10 to the minus 2 molar. Okay. So that's just using Henderson-Hasselbalch to find out ratios and concentrations and things like that. It's not too bad. So this is the last one. I didn't know if we'd have time in class to do it, but we ran out of time. So I'll go ahead and do it here as well. So this one is just some calculations with delta G and how it relates to K, because we kind of talked about K, and how it was related to delta G, but I thought you might want to see an example. So we have an equilibrium constant for a ambiguous reaction. A goes to B, right? And it's reversible. And so K for the equation is 1 times 10 to the positive 5. Yes, that's a very, very big number. So it's a very big K at 25 degrees Celsius. So when you see that, I kind of want you to think, oh my gosh, that's kind of a really big K, right? And remember that K is equal to our products over our reactants. So if K is really big, what's happening here? We're making a ton of product, right? So what's our product? Our product in this reaction, right? A going to B is B. So we are going to have a ton more B than we do A. That's what I want you to think when you see that. All right. So A, if you started with a solution containing 1 molar of A and 1 millimolar of B and let the reaction proceed to equilibrium, what would the equilibrium concentrations of A and B be? Well, you're going to do something really similar to what you did just in number 5, but in equilibrium expression. So we know K equation, right, is B over A. And we know that that is equal to 1 times 10 to the 5, right? What else do we know? We know that the total moles of this solution is not going to change. It's got to stay constant. So we also know that our concentration A plus our concentration B is going to equal to the total concentration. So we know we had 1 molar, 0.000 molar of A, and we know we had 1 millimolar of B, so 0.001 molar, right? So we get them in the same unit. So what is A plus B? A plus B is going to give me 1.001 molar total. This is our total. So now, if we solve for B over here, if we say, what is B? B is 1 times 10 to the 5th times the concentration of A. Okay, now we can take that and we can plug that into, I guess I should carry this down so you can see, we can plug that into right there. Okay, so now we have concentration of A plus 1 times 10 to the 5th times concentration of A is 1.01, right? So it's very similar to what we did just a second ago. So now all you have to do is factor out your A, right? You get 1 plus 1 times 10 to the 5th, 1.001 molar, right? And now we just want to get A by itself. So 1. Okay, so then concentration of A is equal to, and when you put this in your calculator, you should get 1.000989 repeating, something like that, times 10 to the negative 5th molar, right? Okay, so it asked you for A and B, right? What would be the equilibrium concentrations? Okay, so that's A. So how about B? So A, that's not a lot, right? Times 10 to the minus 5. So I'm expecting B to be a lot bigger than that. So go back to your A plus B, right? We know A plus B was 1.001 molar. So then just plug in what we now know of A, 1.000989 times 10 to the negative 5th plus B is equal to 1.001, subtract, and you should get B equal to 1.000989. Okay, so much bigger concentration, right? So almost all of what's there is B, and that makes sense. Okay, so B, let's go back up. They asked, what did it ask us for? Calculate delta G naught prime for this reaction. Okay, so now we know at equilibrium, we're at equilibrium, right? What do we know about delta G? We know delta G is equal to 0. So what can we say? Well, go back to your formula, right? Delta G is equal to delta G naught prime plus RT ln of B at equilibrium over A at equilibrium. Now, we just said we're at equilibrium, so delta G is 0. So plug in a 0 for that, and then just move this. Well, it's don't actually move that over, it's actually move all of this over there, so delta G stays positive. So I get delta G naught prime is equal to negative RT ln of B over A, right? And so I'm gonna replace B over A, right, at equilibrium. What do we call that? We call that ln of K. So I'm just going to leave it there. So you can put KEQ if you want. Delta G naught prime is equal to negative. And remember, R is that gas constant, 8.3 times 10 to the negative 3 kilojoules per mole K, right? Times what temperature are we at? We should be at, did it tell us? So just assume 298. 298 K, ln of our equilibrium, which was 1 times 10 to the 5th, right? Because it was really, really big. Okay, so if you put that in your calculator, you should get negative 28.5 kilojoules per mole. Not too bad, right? Okay, but we're not done. Of course, we're not done. So in cells at steady state, the concentration of A is very different than equilibrium. A is 0.05 millimolar and the concentration of B is 15 millimolar. Now calculate delta G for the reaction. So one more time, right? Go back to that formula. Delta G is equal to delta G naught prime plus RT ln. Now, we're not ln K anymore, right? This is Q. So this is the actual for B and A. So we put actual, right? So delta G is equal to what we calculated here. So negative 28.5 kilojoules per mole plus our RT, so the same thing, 8.3 times 10 to the minus 3 kilojoules per mole K. We're still at 298. I'm gonna run out of room. Let's see if I can scooch that over. Okay, 298 Kelvin times ln 1.5 times 10 to the minus 2 molar over 5 times 10 to the minus 5 molar. And so I just converted those to scientific notation because I don't know. I like to do that, but you don't have to. Just make sure your units are correct. So if one's in millimolar, the other's in millimolar, okay? Negative 28.5 kilojoules per mole. All of this rest of the stuff, you should have gotten 14.1 kilojoules per mole. And so you should get a delta G value that is negative 14.4 kilojoules per mole. And that's it. All right, hope this helped.